Hello everyone, we are Team 20. Our project MultiTask-IEEG-Brain-Decoding. Recent advances in IEG allow us to record high-fidelity neural activities from human subjects, enable foundation models for the next generation of brain-computer interface. However, decoding high-dimensional IEG remains difficult due to signal variability and anatomical difference between subjects. In addition, current benchmarks such as neuroprompt rely on binary classification tasks, which lead to performance saturation when using simple linear models. First, we aim to transition from binary to multi-class classification to provide richer supervision. Second, we incorporate advanced temporal modeling to improve decoding accuracy and to better capture long-range temporal dependencies. Third, we introduce anatomically informed embeddings to align signals across different subjects.
We utilize the NeuroPro benchmark and Braintree Bank dataset, which consists of high-fidelity IEEG recordings collected from 10 subjects as they watched over 40 hours of Hollywood movies, like The Martian or Avengers. The core task is to interpret these high-frequency brain signals to predict 15 distinct multimodal features. This range from low-level visual cues like optical flow to high-level linguistic features like syntax and GPT-2's appraisal. Our goal is to build models that not only decode these features accurately but generalize well across different sessions.
Now I'll present our whole pipeline, a unified framework designed to decode human brain. First, look at the data. We record cortical activity at a high frequency of 2048 Hz, where subjects watch naturalistic movies. To extract the best features, we designed four different pre-processing strategies, ranging from raw voltage to a combination of Laplacian spatial filtering and spectrums. Next, you can see our model zoom. We use the linear model as the baseline to measure the effect of CNNs, transformers, member, and diffusion models. We evaluate these models across 15 downstream tasks using ROC AUC as the unified matrix. Now let's focus on three advanced architecture. First, on the left, we engineered custom spatial temporal positional embeddings, which encode both electron location and temporal dynamics to be better capture structure dependencies in IEEG signals. This allows the model to map exactly where and when a signal occurs. In the middle, we utilize member models. We implemented a bidirectional member, which scans EEG data forward and backward. Our text pre-trained member follows a three-stage pipeline. We initialize from LLM pre-trained weights, adapt them to EEG through unsupervised learning, and then apply LoRa for efficient task-specific fine-tuning. This sequence enables us to repurpose LLM feature extractors for neural decoding. Finally, on the right is MultiDiffNet, our chosen state-of-the-art benchmark. It is a generative diffusion framework that jointly optimizes three objectives: DDPM-based signal reconstruction, classification, and contrast alignment, encouraging the data to learn a subject-invariant latent space.
Here is our result. We evaluated several models across multiple IEG tasks and compared them to our linear baseline model. Across all kinds of models we try, members achieve slightly higher results on most tasks. We think this is because its state-based architecture matches with the temporal dynamic of IEG, so it captures long-range dependency efficiently with relatively few parameters, which help us in the small data and multitask settings. To conclude, our study provides useful insights for model design in this field. The neural sequence models constantly perform better than the linear baseline, and the members achieve a best average performance across tasks. However, there is no single architecture domain, so the model choice still remains feature and task dependent. For our future work, we are going to extend the diffusion model to full 3D spectrum representations and going to explore more advanced precision encoding methods. And for our MABA-based model, we are going to pre-train on a large-scale EEG and ECOG with 2D selective SSM variants.